Hi, I'm Scott Ransom. I'm an astronomer with the National Radio Astronomy Observatory and a professor at the University of Virginia. I study pulsars. I'm a pulsar guy. And pulsars are what's left over after a very, very massive star at the end of its life after it explodes and leaves behind a neutron star. And we see these objects as flashing beacons basically in the sky. And we can use them to do a wide variety of science. So astronomy in general, I've been one of those guys who's been interested ever since I was a kid. Went to space camp, wanted to be an astronaut, did that whole shebang. And then fell in love with physics and science in high school and then in college. And when I started studying astronomy in general, because that was definitely the part of physics that I really, really liked, when I found out about compact objects, neutron stars, black holes, white dwarfs, I completely fell in love. And pulsars, they kind of epitomize the stuff that I like to do because we basically need to use fast computers, we need the most sensitive detectors, and I like hardware and software and stuff like that as well. So it meshes everything together that I really love. A pulsar is a neutron star, which even that is a very, very strange idea. It's basically a gigantic nucleus. So if you take the nucleus of an atom, but add a tremendous amount more mass, basically all the mass of everything that's in the solar system, the sun, all the planets, all the gas, compress it down to the size of a city, then you'd have something that's the density of a nucleus of an atom. And then if you compress in a big magnetic field as well, and then rotate it, so you have incredible density, a huge magnetic field, and tremendous rotation, that causes all sorts of physics to happen, which causes beams of light, which we see flashing like a lighthouse. And so that's basically the way to explain them, cosmic lighthouses. So one of the neat things about pulsars, because these things are spinning, the only energy that they give off, and they have tons of energy that's trapped purely in their rotation. They're giant flywheels in space. The only way that energy is given off is through their lighthouse type emission. So as they're emitting this radiation, they slowly slow down over time, but that's their only energy loss mechanism. And that's so precise, the slowdown is so tiny that we can use them as perfect clocks. So basically they're clocks scattered throughout the galaxy that we can use to test Einstein's theory of relativity, to search for gravitational waves, to do all sorts of amazing measurements by looking at the ticks of the clock that you couldn't do in any other way. So a black hole is very similar actually to a neutron star. Neutron star is the densest thing that you can have that actually has a surface. But if you stick a little bit more mass on it, if you add, if you just keep putting mass onto this ultra dense nucleus of an object, eventually the quantum mechanics, which is holding up that neutron star, eventually it can't hold it up anymore and gravity wins and it will collapse from a neutron star into a black hole. And so a black hole is basically the absence of a surface. And it's it's an object with an incredibly strong gravitational field. But what's going on inside of that black hole, we really do not know and understand. That's beyond basically what Einstein's theory can even tell us. Pulsars are incredibly faint objects. To study the ones that we study routinely, we need by far the biggest radio telescopes on Earth, such as the Arecibo dish, which is built into the ground in Puerto Rico. That dish is 300 meters in diameter, so it's a monstrously large telescope. But even that telescope is not big enough. For pulsars, we need incredible amounts of collecting area in order to get the sensitivity. So what's on the horizon in about 10 years is called the Square Kilometer Array, and it's going to be tens or maybe even 20 to 50 times more sensitive as Arecibo. But that comes with a large cost. It's going to be $3 to $5 billion, so it's not going to be cheap, and we need an international collaboration in order to make it work. I think the big thing that's going to happen really shows what millisecond pulsars especially can let us do as tools to study other things. So there's a big, massive international project going on. And here in the United States, our group is called NanoGrav. And what we're trying to do is use millisecond pulsars spread around the whole sky. And we time each one very, very precisely and monitor it for years. And we're looking for ripples in space-time, which Einstein's theory of relativity predicts should be there, due to massive black holes orbiting each other throughout the universe. So we will be able to measure the stretching and compressing of space-time just by seeing how the timing of the pulses changes between these pulsars. And so that's a direct detection, we believe, of gravitational waves. And it could happen within the next 3 to 5 years. So something I'm personally really excited about is just 2 years ago, in a big survey that I'm part of, we're trying to find new millisecond pulsars in order to do this galactic gravitational wave detection experiment. And we found an amazing millisecond pulsar that's being orbited by 2 other objects. Most millisecond pulsars only have 1 companion star that orbits, but this one has 2 white dwarfs, so it's a stellar triple system. And that shocked everyone because we didn't think these things should really exist. And what's even more surprising, and it shows the utility of pulsars for doing cool physics, is that we think that we're going to be able to test the so-called equivalence principle of Einstein's theory of relativity to an extent well beyond what anyone has ever been able to test it before by looking at this pulsar, even though it's halfway across the galaxy. And I think that's pretty amazing.